Okay, our next, our final speaker in this session is Dr. Sameen from ICTP in Trieste, who's going to talk about stability of channel flow with stratification.
Control? Oh. Okay, thank you. So I'll be talking on the stability of channel flow with a viscosity stratification in the normal direction from the wall, and I'll be looking into the from the point of view of linear stability and transient growth, how they are affected by the stratification, heating in general. So this is a picture most of you know. So when you have very silent channel, you have this mode of transition where you have linear stability and secondary instability, and then goes to turbulence. If you have a little more larger background turbulence, it may take any of the other routes, what we know and what we don't know. And after that, it may be the bypass transition. It bypasses all the known theories. So I'll be looking into the primary and algebraic growth in this talk. So why channel? So we know that the linear instability, from linear instability, the critical Reynolds number is somewhere around 5772. This is done by Ossack somewhere in 72 or something. But experiments have always shown that the Reynolds number to be around 1000 or 2000. And the first blame is always on nonlinear mechanism. But as Henningsen and his group and Landl before have shown that there could be transient growth present in the channel flow, which basically consider the stability equation as an initial value problem, and then goes on to find some algebraic transient growth at a finite time, even though the eigenmodes are individually decaying at infinite time. So the question we pose here is, suppose we have a stabilizing parameter like a curvature or a viscosity stratification, which linearly stabilizes. Will the transient growth also follow the same trend? So in general, suppose we have a parameter, a control parameter lambda, and if the flow is stabilized linearly, will it stabilize non-modally also? But to remind you, this talk is not on flow control, but we are just trying to compare the linear stability and the transient growth in the channel flow. And what can lambda be? We have tried with viscosity stratification with it's a two fluid geometry. You have one fluid going inside the other in a channel, and we found stabilization in the linear analysis, as well as we tried with a shear thinning fluid. Again, we found a stabilization, but when we computed the transient growth, we found practically no change. So we tried with slip velocity in a hydrophobic surface. Again, we found some stabilization, and the transient growth was showing some different trend. We also included wall divergence. Again, we know that it's highly destabilizing from the works of Eagles. Again, here in the transient growth, we found marginally no change. And what I'm going to present here is what happens when the walls are heated indifferently. So the geometry is this. We have a channel. One wall is at temperature T hot, other one T cold. So this generates a viscosity stratification of the Arrhenius type, and your mean velocity profile will be asymmetric. So the peak will be shifted towards the hot wall if it's a model like this, as in water. If it's air, it will be the other way around, because the viscosity will be increasing with temperature, whereas in water it will be decreasing. So in the results I am going to show, we have used the constants here from the water. So this is the modified mean profile we obtained with the viscosity model I have shown. So the viscosity profile will be something like this, if you assume the temperature profile to be linear between two walls. So as you increase the viscosity ratio, which is basically the ratio of viscosity of cold and hot walls, you have a asymmetry building up in the mean profile of the temperature of the velocity. Now you apply the usual way to derive the linear stability equation, and this is the modified Sommerfeld, this is the modified square equation, and this is the energy equation. And the one in dark green is basically the one which contains viscosity gradients without the viscosity perturbations, namely the temperature perturbations, and the blue one will contain the temperature perturbation, and this is the energy equation. So we will do one by one. First we will try to see what happens with viscosity stratification alone, then we include the diffusivity, then we will include the buoyancy and see how does it change. So first the linear instability without the diffusivity and buoyancy. We found that it stabilizes the flow. If you have a symmetric heating, the velocity profile will usually be fuller and there will be a stabilization. But here in an asymmetric heating, we don't know which way the stability is going to be. But here we found that it's stabilizing highly as you increase the viscosity ratio. But coming to the transient growth, we have defined the energy like this, and we maximize the energy, and the gain is defined like this. We found that the transient growth didn't change much, and this is the 2D plot. You have the gain here, you have the temperature here. At some peak, at some time you have a large growth, and we found as we increase the viscosity ratio, there is not much change. And this is the G max, which I have plotted for beta equals 0. Beta is the span-wise wave number, and alpha is the stream-wise wave number. So plotting the contour values of G max, we found there was practically no difference between the 0 stratification and for a very high stratification. So we conclude that for viscosity stratification alone, there is practically no change with the transient growth, and we see that there is no difference between the 0 stratification case coming to these streamwise structures. And streamwise structures, I mean you have the maximum growth somewhere at alpha 0. So it's a streamwise structure that's highly unstable. So suppose we include the diffusivity now. We found that there is no difference in the growth rate, and this has been reported by Wall and Wilson and some others before. So there is no contradiction here. But and we do the transient growth at very small Prandtl number. This case is the same as 0 stratification. It's a plain channel flow. But as you slowly increase the Prandtl number, you see that there is a small span-wise growth that is more unstable than the stream-wise. So somewhere in alpha around 1.5, you have a span-wise instability. And at Prandtl number 1, there is a very large instability that's coming in span wise, and still it's stable linearly. So we say that we found practically no difference in linear mode, but transient growth we have a huge destabilization, and these structures are now span wise. Now, if we include the buoyancy, we found few interesting things. First, at low Grashof number, you have the plane channel flow solution with the good old 5772 here. Now, as you increase the Grashof number, somewhere around 3000, you have a new mode appearing. And if you still further increase the Grashof number further, you have a merging of these two modes, and after 30,000 or so, the unstable mode dominates. Now, if you plot these two values, these two critical numbers, if I call it two critical numbers, you plot that, you see that at small Grashof number, this is the 5772, it goes like this. And the second one is something like this. This could be the Rayleigh-Bernard mode. So we demarcate three regions. One is the plane Poisson flow, then the Rayleigh-Bernard, and Poisson-Rayleigh-Bernard flow. This is at Reynolds number of around 500 or something. And to mention here, Monkiewicz has done a work in which his Reynolds number is around 10 or 12. So he is mainly playing in this region, lower than what we have mentioned here. And his case is to differentiate between the two. His case is actually Rayleigh-Bernard Poisson flow, where we have a more larger inertial forces. Now, what I have shown till now was the unstable stratification, where you have the cold wall on the top and hot wall below. Now, suppose you reverse that. When you have buoyancy, you can do that, which is denoted here by the negative sign in the temperature difference. You see a stabilization of the flow against the Richards number plotted here, which is nothing but Grashof by Re square. So we have two regions. One is the unstable stratification and stable stratification, and this is for the unstable stratification critical Reynolds number, and you see this kind of stability. Now, going to the transient growth, what do we see here? Now, at low Prandtl number, the case is no different. The Grashof number makes no difference. It's the same as the plane channel flow. But as you slowly increase the Prandtl number, the effect of Grashof number also comes up. So, as you increase the Prandtl number, you will see that there is some instability that's coming up in the span-wise direction. And again here the effect of Grashof number is not much. But if you increase still further, you see that the span-wise modes are already taken over the stream-wise modes, and the effect of Grashof number becomes large. So, that is our conclusion. We see that when you have viscosity stratification alone, you have stabilization. When you have transient growth, it's marginal change, and when you have diffusivity, it's a different scenario. When it's a marginal change in stabilization in the linear mode, and it's a huge destabilization in the transient mode, and buoyancy it's the other way around. And that's it. Thank you for your attention.
I just wanted to comment this. The first case that you were doing with just viscosity gradients, that's exactly equivalent to what we were doing with an eddy viscosity that was also fixed. I mean, we had a variable eddy viscosity that was a function of y.
Okay.
And there, if the ratio is large enough, then you do see new instabilities happening near the wall or in the places where the
Linear instability.
no, I mean transient growth.
Ah, okay.
I mean transient growth. But of course, the ratios that you get when you do the eddy viscosity are much larger than yours.
Okay.
The order of 100.
Oh, that's possible because, say for example, you have streamwise streaks. Now your streamwise streaks may not experience the difference in viscosity in this case. In your case,
Yeah, I mean they're essentially new streaks that appear in the places where the viscosity is lower.
Yeah.
But you need higher ratios.
Okay.
Your comment on the marginal change on transient growth has to be interpreted a little bit carefully. I can't generalize my comment, but you also mentioned in effect on a hydrophobic surface,
Yeah.
for which we have done some study. We were quite puzzled because if you look at the actual transition, effect of the hydrophobic surface and transition, quite large. But when we look at the transient growth in the way you look at, which is usually the global optimal growth, total energy growth, has very little effect. And yet, if you look at the transient growth of those energy growth in near wall region where that transition actually more relevant, that actually quite a more significant effect on that transient growth. So perhaps depending on what flow, if you just look at the optimum mode of the total energies at the maximum,
No, you
may
take.
not- it may not be the relevant transient growth you should look for.
No, I think if you take large number of modes, all the modes what you are saying will be included in this.
No, but the transient growth that has a less than global than optimum, but it's a peaks near the wall and that dies rather quickly, get affected by, in the case of, for example, hydrophobic surfaces. That's why it delayed the transition.
Okay.
Even though if you look at the overall transient growth, does not affect at all.
Okay, but I cannot pick up that in this analysis.
No,
Yeah.
I'm not saying
Yeah,
the general,
yeah,
but
yeah,
I'm just
yeah,
kind of a
yeah.
lesson
That's
we learned.
That's possible, yeah.
Okay.
And I have a comment on your work. So you have used this velocity profile.
For model for hydrophobic surface, yes.
Yes, and these people have used this velocity profile. And if you use this velocity profile, your mean will always decrease with Knudsen number. And if you use this, the mean will always, the U will always increase with Knudsen number. But instead, if you use, okay, this is for a divergent channel, but if you use this kind of profile, and if you numerically evaluate, then you will get the exact what's there instead of assuming a analytical equation. That's what we have done in that.
Okay, I think that's a good point to start. Thank you very much for your presentation.